Hi, everybody. My name is James Garland. I use he, him pronouns, and I am a senior at Haverford College. I'm going to be talking a little bit about the work that I've done with Karen Masters this summer, and I'm continuing this semester on the evolution of galaxies and how they interact with their environments. So to start, it can be nice to talk about what we know about galaxies. And a good way to frame this might actually be, what do we know is not true about galaxies? Well, for one, galaxies are not static, so they are evolving dynamic objects. Secondly, galaxies are not closed systems, so they are constantly interacting with their local environment and other galaxies around them. Additionally, and importantly, galaxies are not homogeneous, so they come in many different shapes and sizes and demonstrate a wide variety of behaviors. So putting these all together, we get a scenario where galaxies are not easy to understand. So if we want to understand a little bit more about these features, we can pick a particular property of galaxies to track. One good property to choose for this are bars. So bars are large central structures in galaxies, or in many galaxies, that we have an okay understanding of their behavior. So what do we know is the case about bars? Well, for one, they're formed by kinematic instabilities inside of the galaxy. They drive gas inflow into the center of the galaxy, causing a quick burst of star formation. And this behavior actually quickly suppresses star formation in the galaxy by exhausting that material. And that process is called quenching. So in the context of the previous slide, what can bars tell us about galaxies interacting with their local environments? Well, observed behaviors like what we see on the top right here suggest that bars are suppressed in close pairs of galaxies. However, simulations on the bottom right suggest that tidal interactions with other galaxies form or strengthen bars. So clearly there is some existing tension between these two ideas. How do we go about resolving this? Well, we can combine this tidal interaction bar formation concept with the known star formation behavior of these bars that we discussed in the previous slide and try to form a more holistic picture. Now, if we want to do this, we're going to need a good data set to work with. So we are using the Galaxy Zoo 2 catalog of face-on-disk galaxies. Galaxy Zoo 2 is a completed citizen science project that worked on classifying the morphologies of many thousands of galaxies. To get the best classifications that we can, we impose a redshift limit. Importantly, we have mass value and star formation rate values about these galaxies from SDSS spectra. I'll note here that we're working with specific star formation rate, so that star formation rate controlled for mass. And we also have the total and fiber star formation rate. So total is for the entire galaxy. Fiber is for the central region where these bars primarily lie. And finally, for a technical reason that I'll discuss in the next slide, all the galaxies we're working with have to have at least one neighbor in the nearby redshift range, although they don't have to be physically associated. So this leaves us with a sample of 16,600 galaxies to work with. Now, before we can look at this data and start analyzing it, we're going to have to figure out a way to combine it with that tidal picture we were talking about earlier. And we do this by introducing a tidal strength parameter Q to quantify tidal interaction. So Q tracks the influence that nearby neighboring galaxies have on a given galaxy, and is proportional to the distance between these galaxies, the size of the galaxy that we're looking at, and their relative masses. So on the left here in the sparse picture, we have a low Q situation, where in this really dense situation on the right, it's high Q. So with that in place, we can actually start to look at our data. And this is the most combined perspective of what we have. So on the y-axis, we have star formation. On the x-axis, we're looking at tidal strength, and it's colored by bar likelihood. So the red regions are much more likely to have a bar than the bluer regions. Now, what stands out to us when we initially look at this plot? Well, for one, we notice behavior consistent with quenching like we discussed earlier. What this is saying is that in galaxies that are heavily barred, they're going to have lower star formation rates. However, in this project particularly, we're interested in looking at trends that go with tidal strength. So what do we see there? Well, most majorly, we have a decrease in bar population or bar likelihood in these low star formation galaxies when you move to denser regions. And the same is true somewhat for these higher star formation rate galaxies, although it's not as easy to see in this plot. So to break this down a little bit more, let's look into some separated two-dimensional views of this data. So here on the y-axis, we have the likelihood of having a bar, on the x-axis tidal strength, and we're splitting up our data by star formation rate. So in red, we have high star forming galaxies, and a yellow, low star forming galaxies. In blue, it's the entire population. So for these high star formation galaxies, we don't see too strong of a trend between bar formation, or the likelihood of having a bar, and tidal strength. However, when we look at these galaxies that are not forming as many stars, we see that at high values of Q, there's a significant suppression in bar formation. Now, overall, the entire population of galaxies, we additionally don't see too strong of a trend between these two variables. So what this is telling us is that while there may exist some trends between having a bar and the tidal density of the environment that you're in, there's no clear single global rule for galaxies about this. Now, let's flip this data a little bit and look at specific star formation on the y-axis, tidal strength on the x-axis, and split up by bar likelihood. So if you remember earlier, I mentioned that we have total and fibrous star formation. So that's what we're looking at here on the left and right respectively. On the left, we have the entire galaxy star formation. On the right, we're looking at the central part of the galaxy. So now we have barred galaxies in red and unbarred or weakly barred galaxies in blue and yellow, or green and yellow, excuse me. So let's see what kind of trends we see here. Well, in these unbarred or weakly barred galaxies, we see an enhancement in star formation when you move to high Q for star formation in the entire galaxy. And we see a similar behavior when you're looking at star formation in the center of galaxies. Now let's trace this behavior for our barred galaxies. Well, in the entire galaxy, we have a higher relative increase in star formation in the entire galaxy than we see in the center. So in other words, if you have a bar and you're in these highly dense environments, there's going to be a greater enhancement of star formation in the outer parts of the galaxy than in the center of the galaxy. One possible cause for this might be that in these denser regions, there may be more local gas that can inflow into the outer regions of the galaxies and support the star formation that bars would typically suppress. So to recap really quickly, what have we learned from these data? Well, in passive galaxies, ones that are not forming many stars, bars tend to be suppressed in these denser regions. However, there is no global rule that connects the environmental density and the likelihood of having a bar. However, certain other properties of galaxies, like star formation, may change this behavior. So with that, I'm happy to take any questions. Feel free to contact me on Slack or my email, jgarland@haverford.edu, and thank you for your time.